so a couple of you are curious about how computers work, so I figured I'd talk about it. And it also relates into what we were talking about with electricity, so it's a good little tangent to go on. And I'll also say this video is going to be probably close to 20 minutes long, which I know is a pretty long time, but don't worry, I'll give you, I'll make the points worth it. The points will scale up with the size of the video. And so this could be, and remember, since it's fourth quarter grade recovery time, I'm also going to, help bump up scores from other assignments earlier in the year. So this assignment could really help you out. So hang in there, pay attention. Hopefully you'll learn something and you can answer the questions, and I'll give you points. Okay, so computers. They are all around us. We use them all the time. Like right now, I'm recording this on a computer. You're watching it on a computer. There's computers all around us. We use them all the time without even thinking about it. But what are they? So let's kind of talk about this a little bit more, right? So, like I said, we have computers all over the place, all around us. When I think of computer, this is probably the first thing that comes to my mind. Something like this or this. We've got a keyboard and we've got a screen. We could think of it as we have an input, so you can type stuff on the computer, on the keyboard. You can use the mouse, whether it's whatever it looks like, and you get some sort of output. It will show you some information on the screen, right? So that's like our basic definition of a computer. You put some information in, you get different information out. So we're going to talk about some other examples of computers that maybe you thought of, maybe you didn't think of. Okay, so a phone. Yeah, that definitely fits that definition, right? You can punch buttons on here. It's a touch screen, so you're not really pushing a button, but you can hit different things on there, and it will give you sound and visual information back, right? And it'll even vibrate. That's another way it can give you information. Okay, so that's pretty obvious example. What about a microwave? You can punch numbers on the little screen here, and it will react to that. So I might say 3 minutes 45 seconds, high power, start, and then what does it do? It starts cooking. So it doesn't have it does have a little screen, a little readout screen, but then it also acts on that. It does what you tell it to do, right? So that's another example. What about a car? So I would say the car itself is not really a computer, but it's got computers inside of it. And so, maybe you've worked with Mr. Bennett, or maybe you just know from other experiences that, there's computers inside a car. So your car has little oxygen sensors and temperature sensors, and sensor for how much you're pushing the brake pedal, or the brake pedal and the gas pedal, and all kinds of stuff, right? And so, and it responds to that. And so it might sense, okay, well, it's this temperature, this much oxygen in the air, they're pushing down the gas pedal this much, so this is how much gas I should put in. Taking all that into consideration, this is how much gas we should put into the motor so that it runs smoothly. So that's a computer. We're going to talk, all of these examples here also use the similar types of computers. We're going to talk about some different types of computers in a minute. These all use modern transistorized computers, and I'll tell you what that means in a minute. But what I want you to think about is, can you think of any other examples besides these ones that I gave you here that either are computers or have computers inside that make them work? Okay, so in order to learn about how computers are working, we need to talk about two things. The first one is a conductor. So what is a conductor? You probably learned about this in another science class. I'm not talking about a guy who drives the train. I'm not talking about the guy who stands in front of the orchestra and waves his hands around and tells the musicians what to do. I'm talking about in physics or in electricity. What is a conductor? Then, after you think about it, what is a conductor, we're going to think about, well, what is an insulator? So a conductor is something that allows electricity to pass through it, okay? So if that's a conductor, what do you think an insulator is? Yeah, it's something that does not allow electricity to pass through it. We also use both of these words to talk about heat. So a heat conductor is something that allows heat to pass through it. An insulator is something that doesn't allow heat to pass through it. So if you think about in your house, you have insulation that keeps the heat on the inside of your house and the cold outside of your house. Or vice versa, if it's in the summer, it helps keep it cool inside your house. Okay, so enough with that. Let's talk about the thing that we really want to talk about, and that is a semiconductor. So looking here, we have conductor. We know that means it allows electricity to go through. And we have semi, which means kind of like halfway or sort of, and that kind of thing. And so if I have a semiconductor, well, what do you think that means? Okay, so that, yeah, it means sometimes or half the time or electricity can half pass through or something like that. But yeah, the main idea here is that it's kind of somewhere in between a conductor and an insulator. Sometimes it allows electricity to pass through, sometimes it doesn't. Excuse me. So let's talk about this a little bit more. Let's sum things up with a table here. So a conductor allows electrons to move, electric current can flow through it, and my example for you would be most metals are conductors. There are things that are not metal that can also be conductors, but just an easy way to think about it is, all your metals are going to be conductors. Okay, so then an insulator, if electrons can move through a conductor, do you think electrons can move through an insulator? No, they can't. It does not allow electrons to move. So if it does not allow electrons to move, can there be current? No, there's no current through an insulator. And I'll just tell you some examples of insulators are things like plastic or wood, or most of the time dirt would be an insulator. So yeah, those are all examples of basic insulators. And now let's talk about semiconductor. So I want to know, what do you think? If a conductor allows electrons to move, an insulator doesn't allow electrons to move, what do you think a semiconductor does? Yeah, so sometimes it allows them to move, sometimes it doesn't. So if sometimes electrons can move through it, can there be a current through a semiconductor? Sure, sometimes, right? That's the whole point there. And then I'll just tell you this last one. So some examples of semiconductors would be elements like germanium or silicon. Again, there are other semiconductors, but these are the two that we use most of the time when we're talking about electronics and computers. So, okay, what have I been leading up to? We got this thing called a transistor. And basically what it is it's a semiconductor. But whether or not it is allowing current to flow, whether or not it's acting like a conductor, is controlled by a second electrical source. And so this is what it would look like in our little circuit diagram. Let's dig in a little bit more. Okay, so this side over here, we're going to call this the base. And this is where our on or off signal comes from. So if I apply voltage here, my transistor is on. It's going to allow current to flow. If I take my voltage away, then it's not going to allow current to flow. Okay, we're going to see an example of this in a minute. But just so you know, this other side here, this is called the collector. This is where your sort of source electricity comes in, and then the emitter is where it goes out. And so when it's in here, the transistor either lets it go or doesn't let it go. And this is more what a transistor looks like in real life. This is just for our circuit diagrams. So speaking of circuit diagrams, let's look at one. Here I have a pretty basic circuit built. And let's just kind of see what I've got. So I got a transistor here. You can see this is my base, my emitter, and my collector right there. And plugged into the collector, there's another voltage source. This is 150 volts. So that's a lot. That's enough to shock you and make you not happy. But it's off right now, so we're safe, right? And then this comes out to a switch, and then a little LED light that's off because there's no current flowing right now. And then that connects back around to the rest of our circuit. But up top, I've got another little voltage source that's small. And so this is kind of one of the main things I want to show you about transistors. I have a very small voltage. 5 volts is probably similar to a like a AA battery or something, right? So if you rig things up just right, yeah, you could give yourself a little shock with a AA battery, but it's pretty safe. It's pretty benign. You're not going to really get into too much trouble with a AA battery. This one over here, 150 volts, yeah, that's going to electrocute you. Not fun, okay? So here's the point. Me playing around with 150 volts right here, I'm turning this on and off, that's not very safe because I could accidentally shock myself if I accidentally get in between these two. That electricity is going to flow through me. Maybe even me just touching this and I'm standing on the ground, now the electricity can flow into the ground and, all kinds of bad things could happen. So let's just close that and leave it how it is because we don't want to deal with it right now. Instead, we're going to play with my 5 volts because that's a lot safer. No big deal. I'm not going to get electrocuted by this. I'm not going to kill myself. Still keep teaching physics. Go on and with my life. Everything is cool. But I can use this 5 voltage switch here in my transistor to control the 150 volts. So watch this. When I close this, now current is flowing through here. We got my little light is lighting up. Everything's awesome. I don't really want to come undo this because I'm going to electrocute myself, but if I want to turn my light off, I just open this switch again. And it says, okay, transistor, stop. Stop being a conductor, right? Or say, okay, start being a conductor. So that just kind of gives you an idea of why I would do that. So, okay, sorry, that was a lot, but hopefully you kind of see the basics of how a transistor works now. I'm going to show you a very simple computer. And that is this little setup here. So basically I've got 3 transistors, 1, 2, 3, and a light. And down here, this looks a little bit different from what we've seen before, but this is basically, I can say either low or high, low or high, low or high. And I can turn all of these off and on. So if they're all off, what happens to my light? Yeah, okay, so the light's on. So that's kind of backwards, but I mean, that makes sense though, right? If I have them all on low voltage, my light is on. Well, if I turn any one of these to high, what happened to my light? Yeah, my light goes off. So if I turn this one to high, same thing. Turn this one to high, same thing. So I have 2 on and it's still off, right? So basically the way that this little mini, very dinky computer is set up is that all 3 of these have to be turned off for my light to come on. I know, not very exciting, but hopefully you can imagine scaling this up thousands and thousands and thousands and thousands and thousands of times and having thousands and thousands and thousands and thousands of more resistors, and you can see how you could get a more complicated situation. Like, instead of having 1 light, I could have, a whole bunch of lights. In fact, that's basically what your computer screen is it's millions of tiny little lights set up, and you can turn them on and turn them different colors, and that's all controlled by transistors. So, on that note, let's dig back in with computers and see how things progress here. Okay, let me get caught up on my slides. Okay, so we're going to talk about the history of computers going way back. So this thing here is called a mechanical computer. And you see this, I think it's a lady there, turning this crank. And basically, as she turns the crank, there's gears, pulleys, and levers that are going to move around and do different things. And, one movement controls another, and that's your computer, right? You put in an input where maybe when you turn it, maybe you set some other things over here. Underneath you set a lever, this lever up and that lever down, and then you turn the crank, that's your input, and the output is, it maybe does some very basic math. So these have been around for 100 years, hundreds of years, I should say, and they're really not that powerful. Like I said, they're going to be able to do some basic math, addition, subtraction, multiplication, division. That's about it. Kind of boring, so let's move on. History of computers, first generation. So we don't even really count mechanical computers in this. First generation, we're going to start with vacuum tubes. So what do these look kind of like up here? I think they look kind of like light bulbs. I want to know what you think they look like. Okay, so basically these work the same way as transistors, but they're bigger and they're hotter, and transistors hadn't been invented yet. So that's why they use these. And so they get really hot. That's the downside here. You can't really tell too much from this picture, but this thing is probably, would take up the size of your desk, and it's still only going to be capable of doing some pretty basic math, okay? So, smaller than that mechanical computer, but it's still huge by today's standards, and it uses lots of energy. Not really ideal. So, second generation. Now, we've figured out how to use transistors, and so that's what you see in this picture here. We have a bunch of transistors, probably hundreds of transistors. You can see these guys standing here, so you get an idea of how big this computer is. They're going to put in some input, and it'll spit out like a little piece of paper here with like some information on it, some numbers or something. And so we can basically do the same kind of thing as a vacuum tube computer, but it's just going to use less energy and not make as much heat. But still not very powerful, right? This one would be more powerful than that vacuum tube computer we saw, but just because it's bigger. So for the time, this was crazy. They're like, oh my God, this is amazing that we're doing this. we're a little spoiled today, so we don't think it's that great. Okay, so now, third generation. This is where things start getting interesting. We're still going to use transistors, but we are using what's called an integrated circuit. So we already know what circuit means. What about integrated? Have you ever seen that word or seen it in some other situation? So integrated basically means together, or like put together. And so what we've got in an integrated circuit is we get transistors and wires, and we've figured out how to make them small and small and smaller and smaller and smaller, so they'll fit together on one little plate here. So this thing here is probably the size of the palm of your hand. If that, it's probably smaller than the size of your hand. This is the actual computer there, the processor, and it's probably got hundreds of transistors in there. So way small, right? And so our computers are getting smaller and they're getting more powerful. And so that's pretty cool. That's pretty exciting, right? And so the way that works is with integrated circuits and microprocessors. Micro just means smaller, processor means like the thinking part, right? So it's getting smaller and more powerful. So we've got copper wires, that's our conductor, and we've got silicon, that's our semiconductor. And the way they actually do it is they use lasers to cut little patterns into the silicon, and they fill in some of the holes with copper, and they set it up so that basically you get this one little chip that's got all the information you need and all the little parts of your computer built into it, and it's like the size of your thumbnail or something like that. Okay, and so we call it integrated because we have copper embedded into the silicon, so it's one piece with all the different things on there that you need. Lots of tiny wires and transistors, so we pack a lot of computer power into a pretty small package. So what I wanted to show you based on that was just to kind of give you an idea of how computer power has really grown, how the power of computers has grown while the size is actually getting smaller. So have you ever played, in one of our other videos we talked about the Game Boy, the original Game Boy. I want to know, have you ever seen the original Nintendo Entertainment System? This has been around since before I was born, so they're pretty old, I guess. But I don't know if you've ever seen one of those. Okay, have you ever seen two of those? If you've seen two of those in the same place, that's the same amount of power that NASA had when they launched the Apollo missions to go to the moon. So that's pretty crazy. Like two little, old-timey video game systems were more powerful than everything they used to send people to the moon. Just to give you a perspective on time, Nintendo Entertainment System is probably 35 or 40 years old. When they went to the moon, that was probably 60 or something. Yeah, about 60 years ago. So that's a pretty big jump there, right? Well, let's go on. So this is, I'm going to skip a couple of these. I'm going to look at this one here. So a Samsung Galaxy S6, which isn't even the latest, getting up to S10 now. So this is a pretty old phone by today. That is as powerful as 5 PlayStation 2s. That's what I played with when I was y'all's age. When I was in high school, I had a PlayStation 2. And we thought it was pretty cool. And it was pretty cool back then, but you can see that this smaller phone is like more powerful, right? And so because you need 5 PlayStations to just be the same as one of the phones. So pretty cool. All right, let's keep going down here. This is the one that's the real kicker here. So PlayStation 4, that's been out for, I don't know, like 5 or 10 years. Maybe not 10 years, but 5 years probably, at least. And so they're a little bit old now. But you would need 18,400 of them. So that is a lot. That's a lot of PlayStation 4, right? That would be equal to 1 Tianhe 2 supercomputer. That's like a modern supercomputer, and it's not even the most powerful modern supercomputer. So just to put that in perspective. So it really shows you that computers are getting smaller and smaller and smaller and much, 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 much more powerful. And there's this guy named, he was a computer scientist, last name was Moore, and he was kind of noticing this pattern. This is way back in the 60s. And he noticed a pattern that the number of transistors that they could fit on a chip doubles about every 2 years. And so what that means is that a computer that's the same size is about twice as powerful as, or a computer is about twice as powerful as one the same size from 2 years earlier. Or the other way you could think about it is that a computer that's half the size of one 2 years ago has about the same amount of power. Okay, and that's just because they keep figuring out ways that they can make transistors in the little integrated circuits smaller and smaller and smaller and fit more of them into the same space. And so computers are getting faster and smaller. And that's pretty good, except there's a problem. Right now we're down to where our transistors are about 10 nanometers across. And a nanometer is like real small. To give you an idea, an atom is about a half a nanometer. And so our transistors are getting down pretty close to the size of atoms. But they can't really get that much closer, okay? So, 40, 50 years ago, it might be millimeters across or centimeters across. Now we're down to nanometers. And so we can't really continue this pattern of doubling in power every 2 years because we just can't get any smaller. So within our lifetimes, in the next 10, 15 years or so, we're probably going to see a slowdown in how much more powerful computers are getting. So basically what I'm telling you is that your PS4 or your Xbox, maybe there'll be like a PS5 or like an Xbox 2. I don't know, Xbox has like weird naming systems. So let's just say PlayStation 5. Yeah, there'll probably be a PlayStation 5. It'll probably be more powerful than PlayStation 4. There may be a PlayStation 6. But what I'm saying is there's not going to be a PlayStation 10. It's not going to be that much more powerful than your PlayStation 4. And maybe I shouldn't say there won't be. I shouldn't say there won't be a PlayStation 10. But what I am saying is that whenever they come out with PlayStation 10, the jump from like a PlayStation 2 to a PlayStation 4 is going to be way bigger than the jump from like a PlayStation 4 to a PlayStation 8 or something like that, just to give you an idea. Because we can't make the transistors any smaller. Okay, so things got kind of crazy there at the end. I did lots of talking and I didn't have as many questions to keep you excited and connected. So why don't you tell me this? What do you think is the most important thing, or I'm not even going to say most important. What's your favorite thing that you can do with a computer today in 2020? And on that note, I'm going to end the video. So hopefully you paid attention, answered all those questions. Maybe actually I'm going to ask you one more question too. What do you think was the most interesting thing in this slideshow? Y'all said you were interested in learning about computers, so I kind of gave you a background on it. Hopefully you thought it was interesting. I want to know what you learned. Thanks, and I'll see y'all next time.